Hello everyone. In this series of suspension, today we are looking at the MacPherson Strut Suspension, the front suspension system used in over 80% of all passenger cars globally. Despite being invented in 1947, it remains dominant even in modern EVs. We will cover what it is, how it works, its trade-off, and where it headed. In this slide, we will see the core purpose of the suspension. Every suspension must do three things at once. First one is comfort, load isolation. Second is stability. Third one is handling. In the comfort of load isolation, it absorbs road irregularities and limits vertical acceleration to isolate the chassis from impact. Second is stability, that is contact patch. Maintains constant tire to road contact to ensure continuous traction and braking force. Third one is handling, that is dynamic control. Manages roll, that is cornering, and the pitch, braking and acceleration while ensuring accurate steering responses. What is MacPherson strut? In this diagram, we can see the MacPherson strut. The history of the MacPherson strut is in 1947. It was patented by the Earl S. MacPherson at General Motors for the Chevrolet Cadet project. In 1950-51, the first production application in English Ford console and zipper. Here is the construction of MacPherson strut. It eliminated the upper control arm by integrating the shock absorber, coil spring, and steering pivot into a single unified telescopic strut, each all in one unit. Reduces from front suspension component count by approximately 30% compared to traditional wishbone architecture. This causes less weight, less cost, and much more engine bay space. Here is the anatomy and construction. Top mount and bearing attachment attaches strut to the vehicle body, incorporates the thrust bearing to allow steering rotation under heavy radial loads, and rubber cushion for NVH isolation. Here are the coil spring that supports the vehicle weight and provides the restoring forces. The shock absorber, the strut housing, that is a telescopic damper that controls the spring oscillation and doubles as the steering kingpin. Here is the knuckle, steering knuckle, that connects the strut, lower wishbone and tie rod to the wheel hub. Here are the control arm, that is LCA, a shaped arm connecting the knuckle to the subframe, providing lateral and longitudinal vehicle wheel motion. Here is the working principle and kinematics in action. Here the vertical kinematics, that is jounce and remount. Jounce stand for how much the wheel travel above from the center of the axis of wheel, and rebound from the center of axis how much wheel travel below it. That is, a strut slides up and down in its inner axis. Spring stiffness and the motion ratios are typically tuned to the natural frequency of 1.1 and 1.3 for passenger cars. This ratio makes that there is more stability in the passenger vehicle. Here is the rotational kinematics, that is steering. Unlike, unlike systems with stationary shock, the entire MacPherson strut rotates on its top mount thrust, bearing when the steering tie rod pushes the knuckle. Here is the engineering trade-off. The advantage, the space efficiency, that is a lateral space saving, essentially for a transverse engine front wheel drive cars. Cost and weight, cheaper to manufacture, lighter unsprung mass. This unsprung lighter unsprung mass handles which makes the SUV to handle more efficiently. Packaging, high mounted springs allow for lower aerodynamic hood lines. As you can see in the figure, this is the MacPherson strut, which along with the spring, shock absorber, knuckle, and the tie rod. Here is the compromises. The bending stress. The shock absorber acts as the structural locating link, causing high friction and the friction from side loads. Here the kinematic coupling. Roll center height and the camber gain cannot be tuned independently. These are the problems with the MacPherson strut. Primary application of the MacPherson strut is hatchbacks, sedans, compact SUVs. Here is the comparison matrix of MacPherson strut versus double wishbone. As we can see in the example, there are the board diagrams showing the wishbone and versus MacPherson strut. The camber control. Poor. It is inherent camber loss, typically 0.8 degree per G. Lateral acceleration reduces cornering grip and accelerates outer tire wear. And in terms of cost and packaging, it had low cost and highly compact. In double wishbone system, the camber control is excellent. The short long arm, that is the upper arm, controls the geometry dynamically induce negative camber during the roll, maximizes the tire contact patch. As there is both arm in the double wishbone, by adjusting the upper arm, we can change the camber control depending on our requirement. Here is the cost and packaging. It is expensive as the one more component is added into it. Heavy, limits engine base space. Diagnostics, maintenance and control common failures. First zone is a top mount, that is a rubber cushion. Here are the symptoms of chunkling, knocking, over bumps, binding steering. The causes are thrust bearing wear or rubber distortion, often invisible without disassembly. These are the problems in the MacPherson strut. Also, the second zone is hydraulic seals. Symptoms: visible fluid leakage, fails the bounce test, that is of 1 to 2 bounces. Causes: temperatures cyclic and degraded during rubber seals. Third one is a piston zone, that is a piston rod. Symptoms are friction, uneven damping. Causes are structural bending, stress for lateral cornering, forces causing the internal friction, and uneven wear. The takeaway from this slide is that typical lifespan is of 50,000 to 100,000 miles due to integrated design. Complete unit replacement is usually required upon failure. The future, new energy vehicles, that is NEV. The NEV input. Battery packs added of 200 to 400 kg or 500 kg in long range BVs to sprung mass. That is electronic motors eliminates engine noise make mass. The engineering challenge. The static deflection increases by up to plus 45 mm, bending moments multiply. Tie rod NVH, that is noise vibration hardness, around 80 to 300 Hz, becomes highly prominent in the cabin. Modern solution: lightweighting. Stampede steel lower control arms replaced by aluminum 6061 T6, that is 34% lighter, or short class fibers polyamide, that is PA66, or 45% lighter. Smart damping, that is integration of active electromagnetic dampers to manage it lightweight without ruining the ride comforts. These are the electromagnetic dampers which adjust the using a magnetoreological fluids inside the damper to adjust the damping cushioning of the property of the suspension by the electronic system. In the NVH tuning, upgraded hydraulic damping elements and acoustics tuning to block high frequency transmission paths. Here are conclusions and references. First conclusion is architectural efficiency. MacPherson's invented in 1947 integration of shock, spring, and pivot remains the gold standard for packaging and cost. Second is the kinematic compromise. It trades the superior camber control and double wishbone for reduced weight and unparalleled engine base space. The new NEV evolution, despite 80-year-old mechanical roots, AI-optimized geometries, active dampening, and aluminum composites ensure it dominates in EV era. Here are the references which I have used to make this video. You can visit this site to check all the data mentioned in the slides. Thank you for watching.